Thank you, Chair. And let me thank the organizer and especially Professor Lev for inviting me here. Good morning to people from US, good afternoon to people from Europe, and I'm from Beijing. So in this talk, I'm going to tell you something about entanglement, Wilson ratio, and quantum phase transitions from computational approaches. And these works are done with several groups. One is Professor Sijian Gu's group at the Chinese University of Hong Kong. Then is Professor Guan's group in Wuhan, and also Professor Norma from Warwick. So, oops. Okay. So I'm going to start very brief introduction, then talk about entanglement and the quantum phase transition in two simple examples, followed by Wilson ratio also into solver models. And I don't think I have time to talk about SH model. And so I may just cut my talk by brief summary. So the quantum phase transition is a phase transition induced by the change of system parameters at zero temperature. So usually it will accompany by a change of symmetry in the ground state. Now, if you do computation, so you work at any finite system, then it requires that either ground state is degenerate or there's level crossing at a transition point. So we all know this quite rich phase diagram, and we want to know what happened around the horizontal axis. So when you change doping, the system enters into different phases. So that's what we call quantum phase transitions there. Now, traditionally, people use Landau symmetry breaking theory to study phase transition. For example, in this picture, on the left, all spins are randomly oriented. So there's a corresponding order parameter called magnetic moment. Now, on average is 0. So, and the free energy is minimum at m equals 0. Now, on the right, when m, the magnetic moment, is either m0 or minus m0, you reach the minimum in the free energy, and that we have the finite value of order parameter, and this is symmetry breaking. So in Landau's symmetry breaking theory, very important quantity is this order parameter. So before you write down the free energy, you do need to know something about order parameter. Okay, and once you know the order parameter, you can study all kinds of phenomena you like. For example, you can study the correlation function, and there you make a judgment whether the system has long range order, short range order with algebraic decay or no correlation, etc. All right. Now, however, there are systems where you may not, to write down, or may not so easy to write down order parameter, such as topological phase transitions. All right. Now, in the old, for traditional model, the traditional approach are very successful. For example, in this ID model, we all know about it. Okay. Then so you can also find many other examples of this Landau's symmetry breaking theory's success, and it provides a convenient theoretical framework for quantitative analysis and of the phase transition, and also for some definitive quantities for experimental to measure. However, as I mentioned, there are systems where order parameter, especially local order parameter, is very hard to define. Okay, so for example, in spin liquid, topological order. So whether we can look or detect quantum phase transition without knowing order parameter in advance, and the answer for us is yes. Okay, there are many examples, and today I will show you two. One is from quantum information point of view. By study entanglement, we can detect where quantum phase transition is occurring. The other one is by studying Wilson ratio, which comes from thermodynamic quantities, and also we can detect where the quantum phase transition occurs. So let's start this entanglement. All right. So in the from quantum information point of view, people already did a lot of work. There exists many works exploring a relation between quantum entanglement and quantum phase transitions. Many concepts used in quantum information, such as von Neumann entropy, concurrence, local entanglement, negativities, are being explored. All right now, so if you want to study this entanglement, then you need to have some kind of measures. For example, von Neumann entropy for pure state, and for two-level state, the most popular one is concurrence. Okay. Now, for other many-body systems, you can also use different measures, such as local entanglement, block entanglement, etc. Okay. So today I'm going just to use concurrence for two-level system and local entanglement for fermionic system to show you. All right. So let's start. What is definition for concurrence? So please, suppose you have a system. Now we consider qubits A and B, right? Which is 2 by 2. Then total is 4 by 4 system. So you can write down a reduced density matrix. All right. Then you diagonalizing this reduced matrix, and you get 4 eigenvalues, right, such as here. And the concurrence is defined in this formula here. Right. Then if this concurrence is 0, which means A and B is not entangled at all. If the concurrence CAB is 1, it means A and B are maximally entangled. All right. For example, the spin diamond, when it is a singlet and or triplet, is maximally entangled. All right. Now, and this entanglement, this definition, they somehow relate to each other. For example, this concurrence is also related to this entanglement by entropy definement, entropy definition. Right. Now, so it also, if you work on a spin system, you will find that it also connect to the ground state energy and correlation functions between subsystem A and B, as shown here. All right. Now, if you look at examples, for example, this spin dimer, immediately you will calculate. You find the concurrence is 1. All right. Now, what I'm going to show you, the first model is this familiar XXZ model. You have spin interaction on XY direction and spin interaction in the Z direction. Then you vary the parameter of spin interaction in the Z direction, and you will encounter the ferromagnetic Heisenberg model, XY model, anti-ferromagnetic Heisenberg model, and also Ising model. Right? And it is known that when JZ is very reactive, the ground state is ferromagnetic, and the ground state is highly degenerate, and the quantum phase transition is induced by this ground state level crossing. Right. Now, when JZ is larger than -1, so like I'm showing this picture, for example, from -1 to infinite, then analytically you can show that the ground state is always long degenerate. Right. However, the first excited states are triplet, and they are degenerate at Heisenberg point, anti-ferromagnetic Heisenberg point, as shown here. And the quantum phase transition at anti-ferromagnetic Heisenberg point is induced by the crossing of the first excited state. Also, even it has been shown. Now, if I calculate concurrence, as I show you how to do this calculation, on either you buy Monte Carlo, or you buy exact dimension, or you buy Bethe Ansatz, you get this result. And as show you in this picture, you see that the concurrence is maximal at antiparabolic Heisenberg point, which is quantum phase transition, right? And the concurrence derivative diverges at ferromagnetic Heisenberg point, right? Because many ground in the ground state is highly degenerate, right? Now, and also you can do more careful study, and you find that for one dimension, this XXZ model, because you can solve it by Bethe ansatz, then you can calculate as concurrence analytically, and we find that at Heisenberg point, it is a continuous function, right, as shown in this inset here. However, if you go to 2 dimension, then you find that the concurrence is not analytical at antiparabolic Heisenberg point. However, it is still maximal, okay, when quantum phase transition occurs there, right? And you do spin wave theory, you will get the same answer. And for 2D, we did exact diagonalization for 4x4 and 6x6 as compared to spin wave theory. Then for 3D, we cannot do exact diagonalization calculation. Then we do spin wave theory, and you see that again the concurrence reaches maximum at the phase transition point, and its derivative diverges because it's not continuous there. So brief summary says that we found that in the XXZ model, a concurrence, which is a measure of the entanglement, reaches maximum. Okay, and for one dimensional, it is continuous function, but for 2 and 3D, it has singular behavior. And later, we show that this singular behavior is related to the existence of long-range order in 2 and 3D. All right. Now, let me go to Fermion model by looking at the extended Hubble model. All right. Now, this is extended Hubble model. Now, because I cannot use concurrence. As I said, concurrence is only for 2 level state. Rather, for Fermion system, each side has 4 degrees of freedom. So I'm going to look at a different thing called local entanglement. What I'm going to do is I just look at one side, okay, and its correlation with the rest of the system. So what I'm doing is I calculate ground state wave function. From there, I calculate reduced density matrix. I calculate density matrix. Now I integrate out all degrees of freedom except one side, so which is a reduced density matrix, and that is a 4x4 matrix. From 4x4 matrix eigenvalue, I construct the von Neumann entropy, such as here, and this is what I call local entanglement. Right now, for the extended Hubble model, many people in the audience already know the phase diagram is very rich. For example, this is the phase diagram of one-dimensional extended Hubble model at half filling. Then you can see there are charge density wave, there are spin density wave, there are phase separation, and there are superconducting phase, all showing here. All right. Now, if I calculate the concurrence, local entanglement, all right, and plot as function of U and V, which is 3D plot, then I project it to the 2-dimensional, and you will observe that at the extreme point of this local entanglement, right on the phase boundary of this 2D UV plane, all right? And for superconducting phases, because it involves more than one side, then if I calculate 2 sides, this entanglement called block entanglement, then I also will get the phase. All right. So in other words, for the Fermion system, I also show that I can use the measure of the entanglement to identify where quantum phase transition occurs. All right. And in recent years, last year and this year, we also did the work saying how we can, once we find the next phase transition, then we can construct autoparameter from reduced matrix spectrum, right? So in other words, I don't go from a traditional Landau's approach to use local to construct free energy by local order parameter, then study phase transition. Rather, I use a quantum information concept to identify where quantum phase transition is occurring. Then I, from reduced density matrix, I construct the order parameter. All right, but then this work is not what I'm going to say today. So now, next part is I promised will show you another quantity is with Wilson ratio, and I'm going to show you that we also can use Wilson ratio to identify quantum phase transitions. This work is done with Professor Guan's group, right? And he has a big group, and they worked with beta ansatz for many years, and they can solve as a finite temperature beta ansatz to very accurate, to have very high accuracy. So again, I'm going to show you two examples. One is one-dimensional XXZ model, and the other one is two-component Fermi gas model. All right. Now, the reason we use Wilson ratio is that in experimental measurement, all right, the system, the many-body system we're considering is very complicated. There are many fluctuations and all errors in the measurement. So if you want to use something has global to get a global picture, it is preferable to measure thermodynamic quantities rather than local quantities, right? Because thermodynamic quantities only depend on the external variables, but not depending on system details. And the Wilson ratio is exactly such a quantity as I'm going to show you. All right, now we know Wilson got his Nobel Prize for his many outstanding work, especially renormalization group studies on the Condor model. All right, the Condor model has been shown that it's unperturbed. And Wilson's work is to calculate the TK and also other quantities by an explicitly formula of RG theory. In Wilson's calculation, one quantity is very important is that besides all the constant, as I show here, besides all universal constant, the magnetic susceptibility over heat capacity divided by temperature. And this quantity is Wilson ratio, right? And Wilson in his renormalization group calculation show that in very low temperature, this quantity tends to constant, as shown in this table. You see, he's doing this renormalization, and this quantity approach to 2. All right, and we are going to test. We are going to use Wilson ratio to this system, which is one-dimensional spin one-half chain. Now, if you look at this parameter, the intra-chain coupling is much larger than the interchain coupling. So it is quasi one-dimensional and it can be described by this Hamiltonian. Right. Now, this Hamiltonian can be solved by beta ansatz, and also can use the final temperature beta ansatz, and from there you can calculate energy as a function of temperature. Then you can calculate susceptibility. You can calculate heat capacity, right? Like I show here. So in this picture, I show you three kinds of data. One is the numerical solution of the beta ansatz equation. The other one is analytical solution, not to all the temperature, but to some at some point where you can do a series expansion. And then the data points are experimental measurement. You see they all fit very well. Right? So from analytical result, we can obtain this critical exponent as I shown here. Right? So the result fit with experiment. Now we are going to use this data, the susceptibility and the heat capacity, to calculate the Wilson ratio. And the data is shown in this picture. Right? So on the horizontal axis is the magnetic field. Along the vertical axis is temperature. Then the Wilson ratio is represented by the color. You can see immediately there are 3 regions on this picture. Just look at the color of the Wilson ratio. Right? So on the left is thermonuclear liquid. On the right is ferromagnetic. Okay, like a one-body problem. Then in between is critical region. And this heat capacity and sensibility behavior are obtained by analytical expansion of beta ansatz. So suppose we don't know auto parameter at all. Okay, we just do experiments, measure heat capacity, measure magnetic stability, then we calculate Wilson ratio and plot as I'm showing here. Then anyone can see there are 3 different regions, and also can see the boundary where quantum phase occurs. So this is the beauty of use Wilson ratio. Now, if you do more study, you find that Wilson ratio is actually related to this kappa mu. Okay, kappa rho. This is the single parameter used to define phases in thermonuclear liquid. All right. Now, if we look at in more detail, for Fermi liquid, okay, we have this quasi-particle. Okay, we have this interaction just along Fermi surface, was a well-defined Fermi surface. Now, for Luttinger liquid, there is no Fermi surface, right? And the spin charge separated, right? And also the weight of quasi-particle is 0 at the Fermi, the original Fermi surface. However, these both Fermi liquid and Luttinger liquid has something similar. For example, the specific heat is linearly dependent on the temperature, and the sensibility and the compressibility, they are both independent of temperature. So that's why the Wilson ratio can connect both pointing together. Right? So like I show here, you calculate Fermi liquid, you calculate Luttinger liquid, and you find that, okay, this Wilson ratio all can be expressed by this microscopic parameter. Okay, for example, in the Luttinger liquid, it's all represented by this spin and charge excitation speed there. And usually, you can use the Wilson ratio to characterize the system, whether it's a free particle or strongly correlated. Right. Now, if we go back to look at the thermodynamic quantities, then you find that when the system can be described by this Gibbs energy, energy, particle number, external field, magnetic field at final temperature. Then the spin fluctuation actually is presented by the sensibility, and thermal fluctuation is presented by heat capacity, and the particle number is presented by this compressibility. So the Wilson ratio, as defined at Wilson, which is magnetic susceptibility divided by heat capacity, actually represent the ratio between spin fluctuation and thermal fluctuation. Then similarly, we can also define another Wilson ratio, right, which is the particle number fluctuation divided by thermal fluctuation. Now I'm going to look at these 2 Wilson ratios in another software model, which can be experimentally realized by cold atom systems, as I show in this picture. Then you use optical lattice, then you can build up in 1D, 2D, or even 3D is systems for simulation. The model we are looking at is 2-component Fermi gas. This is a very old model, has been studied by many people. In the old days, it's called, it can be solved by the beta ansatz. In the old days, is studied by Gaudian and Young. All right, now this model has a kinetic energy and the particles are interact by contact potential. It's a delta function here. Now, this model has two kinds of particles, one spin up, spin down. All right. So you can use beta ansatz to find the various phase, as I shown here. The particles compared, such as BCS state, and conform normal, this like a ferromagnetic or one particle state, or in between, so-called FLO state. There. All right. Now, once you write down beta ansatz, and then everything can be obtained by these linear equations by solving this KJ here. Now, we may change the presentation to a little. So rather than talk about spin up and spin down, we can say a single atom, okay, unpaired or paired atoms. Right? Then we can calculate susceptibility and heat capacity and also compressibility. Right? Now I'm showing you here some results by the expansion, either strong coupling, which is when G is very large, or weak coupling case. Right? And also show you in this analytical solution and compared with numeric solution, you can see they fit very well. Right? Then when calculate heat capacity, also like shown here, represented by the excitation energy in the charge branch and also excitation energy in the spin branch here. Right. Okay, so finally, the Wilson ratio is defined by this formula. Okay, here it depends on the spin as density stiffness as well as sound velocity. All right, now this is the result I'm going to show you. If I use Wilson ratio as defined at Wilson, which is heat capacity is magnetic susceptibility divided by the heat capacity. Again, in this figure, on the horizontal axis is magnetic field. On the vertical axis is temperature. Then the color represents the value of Wilson ratio. Okay, immediately you see on the left, it's almost the same color. Right? This represents the phase where all atoms are paired. And on the right, also, it's almost a constant. It represents all atoms are unpaired. And in between, they are paired plus unpaired and form Luttinger liquid. Now, between phases, you see anomalous behavior of Wilson ratio, which represent heat phase transition. So again, without any detailed study, you just measure heat capacity and magnetic susceptibility. Then you plot Wilson ratio. You will see different phases, and also you notice where quantum fission occurs. Now, if you want to know detail, then you have to do more studies. Okay. Now, this picture is obtained by calculating Wilson ratio as defined at Wilson. However, in this case, actually particle number are changing. So if I use different Wilson ratio, as I said before, I use Wilson ratio as defined by the particle number fluctuation over some fluctuation, and then this is the picture I will get, and which is much more clear than before. Okay, you also see in this phase vacuum, then all are unpaired, and all atoms are paired, and then partially paired is FLO state. And in these four phases, the Wilson ratio is almost a constant, right? The same color. And in between, you see very anomalous behavior. There's a very large value of Wilson ratio, and it clearly indicate quantum phase transition occurs. We can make our data, we can do similar calculation for a real system. So on this left figure is obtained by the experimental measurement. Then we follow, use the data and plot on the right. You can see very similar. Okay, so this is what we like to say. Because the Wilson ratio is a sum that is obtained by measure magnetic stability, heat capacity, and compressibility. Now, this Wilson ratio is a single quantity, but its behavior can tell us very clearly, okay, where quantum phase change occurs. Right? Then this concept, this Wilson ratio was also being measured in like other system, like spin lattice system. Okay, and I also show this behavior. Now, at least for the models I show you, we use Wilson ratio to unify this Fermi liquid and Luttinger liquid. Right? Then, if you look at like a Kitayama model, then you can study Wilson ratio, and this is what the work we are doing. Now, our hope is that we also can use Wilson ratio, a single quantity, to unify this measurement in a Fermi liquid, Luttinger liquid, and spin liquid. Right. Okay. Now, also we can for next 2 minutes I can also show it's not just these two components. For W component system, also we did a test. Right. Again, we do this beta Ansatz type of studies, and we can do some analytical expansion, and this is a result for W components, Fermi gas, and the Wilson ratio. Right. And then we plot as function of magnetic field and also temperature. Again, you see quite clearly they are different phases and where phase transition may occur. Right. So to summarize, by studying this 1D interacting system analytically and also numerically, and the scaling laws and the crossover and also can be analyzed, we show that experimentally measurable quantity, okay, the magnetic stability, the heat capacity, then calculated Wilson ratio could be used to characterize phase of quantum liquids. Okay, now this approach is not just for fermions. It can also apply to spin systems, also can apply to boson system and cold atom system with mixture of spin and bosons there. Okay, and then we are from there we can do more detailed studies such as quantum criticality, critical exponents, and etc. This case. All right, and I think I better stop here and thank you for your attention.